So good morning, I'm Kiran Kumar. We working as an assistant professor in Department of ISC. So I'll be handling DAF for you. Okay, so today's topic is here we are going to see various important problem types and a little bit we are going to see about algorithmic efficiency analysis. In important problem type, there is a sorting, where sorting, searching, string processing, graph problem, combinatorial problem, geometrical problem, numerical problem. So the sorting problem, it's going to ask us to rearrange the element, that is the sorting. Either you can sort the alphabet, you can sort the number, and there are character strings. Okay, and then records similar to that of what is being maintained by schools about their students, then companies about their employees. Searching, that is you're going to perform a searching, that is you're going to select the key element. Okay, you're going to select the key element and then you're going to select the key element at a particular position. Next, a string processing is nothing but finding a substring in a given string. Okay, where it's a sequence of an alphabet and then there's a text string. Okay, there's a bit string and there is a gene string. Okay, mainly string matching problem, that is searching for a given word in a text, will be using the string processing. Next, the graph problems that we are going to study in future, DFS, BFS, the topological ordering, everything is with respect to the graph problem. The graph can be thought of as a collection of point called vertices. Okay, it is nothing but if there's a connection between two vertices, then that is nothing but what you call it as an edges. Next, a basic graph include a graph traversal algorithm, a shortest path algorithm, and a topological sorting. Combinatorial problem, that is where you're going to find an approximate solution for the problem, where you can't find out an exact solution, where you're going to get an in terms of points. Okay, next comes the geometrical problems, where geometrical algorithm deals with geometric objects such as point, lines, and polygons. So here we are going to go with the closest pair problem and convex hull problem. Okay, these two are the geometrical problems where you're going to find out the endpoints in a given plane and which are the closest pair among them. Okay, similar to here finding out the closest pair. Next is a numerical problem where there are another large area of applications where problems that involve mathematical objects of continuous nature, like you're going to solve the problem, you're going to solve the systems of equations where you're going to calculate the integrate, where you're going to apply the integration or they're using the definite integrals and evaluating functions and so on. Next, we look at the fundamentals of analysis of algorithmic efficiency. Now, what is the issue? The correctness, time efficiency, space efficiency, and optimality. These are the issues. And what are the approaches for that? Theoretical analysis and empirical analysis. Now, what do you mean by a theoretical analysis? The time efficiency is analyzed by determining the number of repetitions. So that's what we saw in analysis of mathematical analysis of recursive and non-recursive algorithm. Okay, and then here it's the basic operation. That is how many number of times the basic operation gets executed. Now TFN is a runtime, C is the execution time for a basic operation. Next, these are the input size, that is n, and this is number of times the basic operation gets executed. Okay. Next, this is the input size and basic operation. These are the few examples. Okay, the problem searching for a key in a list of n items. Okay, the input number of list item n. Next, basic operation as a key comparison. Matrix multiplication, multiplication of two numbers. Next, checking the prime numbers. So number of digits, that is in a binary representation. What you are doing that you are dividing. Okay, you're forward dividing and counting the numbers. Next, typical graph problem with respect to vertices and or edges, visiting a vertex or traversing an edge. So this is nothing but a basic operations and then input size with respect to the problems. Next, what do you mean by an empirical analysis? So till now we have seen what do you mean by a theoretical analysis, but here we are going to see what do you mean by an empirical analysis. That is, you're going to select some specific sample of input, then you're going to use that. Okay, then you're going to use what is the time you're going to find out the time taken. Okay, that is then you're going to analyze the empirical data. Okay, that is, you're going to provide the inputs. Say for an example, for the Mozart and quick start, n should be greater than 5000. So you're going to enter the 5000, and after entering the 5000, you go on entering the 5,000, 10,000, 15,000, 20,000, 25, 30, 35, 40, and then you're going to get some times. You're going to get the for this, for 5,000 input, what will be the 10? For 10,000, what will be 15? What will be 20? What will be? Okay, and then you're going to analyze the empirical data. Now, efficiency, worst case efficiency, that is, if the problem is of size n, and if you're searching an element, if the element is found at the last, or if it is not found, there is nothing but a worst. Best if it is found at the first position. Next, amortized efficiency. It applies not to a single run, but rather a sequence of operation, okay, performed on the data structures. Next, this is the best case, worst case, and an average case. Worst case will be done C worst, best case C best, average case C average. The number of times the basic operation will be executed on a typical input. So not the average of what's done the best case. Expected number of basic operation considered as a random variable under some assumption about the probability distribution of all the possible input. So average equal expected under uniform distribution. This is with respect to a sequential search. In terms of a sequential search, you go on searching an element one by one, or nothing but a linear search. Now here, what is the worst case? The worst case is nothing but you're going to compare, you're going to do all the n comparison. Then what is the best case? Best case, you're going to compare at the first element, and the element is found out. Next, what is the average case? Average case, you're going to find out n plus 1 by 2. Okay. Now what is the exact formula? For basic operations count, C of n equals n into n minus 1 by 2. Okay, then formula for indicating the order of growth with specific multiplicative constant, it is C of n equals 0.5 n square. Then formula indicating order of growth, that is C of n equals C of n square. Okay, next, what is the order of growth? Order of growth within a constant multiple as n tends to infinity. Example, how much faster will the algorithm run on the computer? That is twice as fast. Okay, that is, you're going to develop an algorithm with a 1 gigahertz processor. So you're checking how well it fares well on a 2 gigahertz processor. Next, how much longer does it solve the problem of a double input size? Now this is some of the order of growth, where if the value of n is given, so substituting the values, so what values you're going to get. Okay, then this is some properties where f of n belongs to O of f of n. Okay, so these are some of the properties. Next, establishing the order of growth. This is for T of n and G of n. Okay, it is 0. If the order of growth of T of n is less than order of growth of G of n, that is, if the time complexity is less than that of the order of growth G of n. C greater than or equal to 0. Order of growth is equal to order of growth of G of n. Next, if it is infinity, order of growth T of n is greater than order of growth G of n. Okay, then using the L'Hospital's and strings formula, okay, we can solve some problems. Okay, next, all algorithmic function belong to the same class. All polynomials of the same degree belongs to the same class. So there are some class of problems. Next, exponential function have different orders. Okay. Next, this is a basic asymptotic efficiency classes, which is very, very important. One constant, logarithmic, linear, n log n. Next, n square is a quadratic, n cube, cubic, 2 per n exponential, n factorial is nothing but a factorial. Okay. Next, these are the references. So thank you.